Good evening, ma'am.
Good evening, sir.
Can I start, ma'am?
Sir, you can start, sir.
Okay, thank you. Good evening, student.
Good evening, sir.
Yes, student. Today we are going to start our discussion on electromagnetic waves. So, do you know anything about electromagnetic waves? Whatever comes to your mind, you can tell me, no issue. Electromagnetic waves. Whatever comes to your mind, you can tell me, no issue. Yes, student. Do you know any properties of electromagnetic waves? So, as the name suggests, okay, the vibrations of electric and magnetic field vectors generate the electromagnetic wave. It's there in the name itself, it's there in the term itself, electromagnetic wave. When you separate this term, you will be getting electro and magnetic. So, electric and magnetic field vectors, when they vibrate in space, that generates actually the electromagnetic wave. And the visible light, okay, with the help of which we see objects around us. So that visible light is also a part of this electromagnetic spectrum. So spectrum means visible light is not only the type of electromagnetic waves. We have radio waves, we have X-rays, we have infrared rays, we have ultraviolet rays. So all these radiation, they come under the category of electromagnetic waves. Okay. So before moving forward with respect to the formulas and equations, first of all, I would like to tell you something regarding the displacement current. Okay, displacement current. What is meant by displacement current? What is meant by displacement current? So you all know very well about the concept of capacitor. Okay, so when a capacitor is actually charged, okay, when a capacitor is actually charged, you will be getting a change of electric charges there, or a change of electric flux. Okay, so you all know very well about the parallel plate capacitor. So these are the two plates of a parallel plate capacitor. Okay, so whenever this capacitor is charged, so say you are having positive charges, okay, on this plate and negative charges on this plate, like that. So whenever this capacitor is charged, you will be having some electric field in between the two plates. Okay, due to the accumulation of charges, you will be getting electric field in between the plates, and that electric field or electric flux, to be more precise, that electric flux is changing with time. Okay, because of the change in the value of charges stored in the capacitor plate. Here you will be getting a time varying electric flux. Okay, a time varying electric flux existing between the plates of the capacitor. So a time varying electric flux. A time varying electric flux exists between the plates of the capacitor. Due to the charging of the capacitor. So due to the time dependent electric flux, okay, you will be getting a current called displacement current flowing between the two plates of the capacitor. So that current due to the time varying electric flux in the capacitor is actually called displacement current. Okay. So displacement current is nothing but the current that is flowing between the plates of the capacitor. Okay. So it flows between the plates of the capacitor due to the time dependent electric flux. So that is called displacement current. Okay. So the concept of displacement current was actually proposed by Maxwell, who was a scientist actually. So he gave this equation actually. So the equation for displacement current was given by Maxwell, the scientist. So the displacement current is indicated by I suffix d. So that is given by epsilon naught d phi e by dt. So here what is the meaning of epsilon naught? That is the permittivity of free space or vacuum. That means when the space between the plates is filled with air or vacuum, you will be having this much of permittivity value, and phi e is nothing but the electric flux. Phi suffix e is nothing but the electric flux. So the differential of this electric flux with respect to time multiplied by epsilon naught, it gives you the displacement current. Okay. So after proposing the definition of displacement current, Maxwell actually gave a different form of Ampere's law. So that Ampere law is nothing but integral B dot dl is equal to mu naught into IC plus ID. Okay. So usually in Ampere's law, we used to write integral B dot dl equal to mu naught into I. Okay, we don't separate the I into IC and ID. But Maxwell actually proposed the concept of this displacement current existing between the plates of the capacitor. So when the displacement current flows between the plates of the capacitor, then only the total current can maintain continuity in a circuit. So Maxwell actually included this term displacement current in Ampere's law, and actually the discrepancy in the Ampere law was actually rectified by Maxwell in this way. Okay. So this formula for displacement current is included in this equation, and now the modified equation for Ampere's law. Okay. Modified Ampere's circuital law is given by modified Ampere's circuital law is given by, so integral B dot dl is equal to mu naught into IC plus epsilon naught into d phi e. Okay, d phi e by dt. So this is the modified form of the equation. Here IC is nothing but the conduction current. Conduction current is the normal current. Okay, we know very well the flow of electron contributes to electric current. So this IC is nothing but the conduction current So that current is the current flowing through a wire. Okay, when you give a source of battery to the wire, you can observe the flow of electrons in the wire, and due to the flow of electrons, you will be getting the conduction current. So that current is represented by IC, and displacement current is the current flowing between the plates of a capacitor due to the change of due to the change of electric flux. Okay, due to the change of electric flux between the plates of the capacitor. That is called displacement current ID. So ID equal to epsilon naught into d pi e by dt. This is the concept of displacement current. Okay. And do you all understand this concept, students? The concept of displacement current, do you all understand this?
Yes, sir.
Any doubt up to this point?
No, sir.
Okay, fine. Now I will be giving you some more details regarding this displacement current. Okay. So some more details I will be giving you. So this ID is equal to epsilon naught into d pi e by dt. So this electric flux, according to the Gauss law in electrostatics, according to the Gauss law in electrostatics, the electric flux is given by electric field multiplied by area. Okay. So when you include this pi e in this equation, actually the equation for displacement current is modified like this. ID equal to epsilon naught into d by dt of E into A. So here your area is constant, so area can be taken outside and the electric field is actually varying. So this is another equation for displacement current. Okay. And in between the plates of the capacitor, okay, in between the plates of the capacitor, the electric field is given by. So at a point in between the plates of capacitor, your electric field is given by E equal to sigma by epsilon. Okay. Sigma is nothing but surface charge density. So charge by area actually. So charge by area means, so that is Q divided by A. So already you have epsilon naught. So E equal to Q by A epsilon naught. And from this, your equation here is modified. So ID is equal to epsilon A into d by dt of, instead of electric field you need to substitute Q by A epsilon. Okay. So once again, what you can do is, you can actually take the constant terms outside. So when you take the constant terms A into epsilon naught outside, you will be getting ID. Okay. ID is equal to dq by dt. Okay. ID is equal to dq by dt. How we can arrive at this equation? Here you see A into epsilon naught is constant, that can be taken out of the differential. So A epsilon naught and A epsilon naught will get cancelled. So ID is equal to dq by dt. So here from this equation, we can understand that the dq by dt is nothing but the usual current which we are talking about. Okay. So IC is equal to dq by dt. IC is also dq by dt. And here also we got ID is equal to dq by dt. That means ID is equal to IC. So here this is how we can understand that the current flowing through a circuit is continuous. Okay. So this is the property of continuity of current. So this is how you need to understand the concept of displacement current. And few more equations we are going to discuss now regarding the displacement current. What are the equations? That is, we know very well Q equal to T into V. Okay. This is the expression connecting the charge and the potential difference of a capacitor. So Q equal to T into V. And we know very well that ID equal to dq by dt. Just now we have discussed. So instead of Q, you are going to substitute C into V. Okay. C into V. So here the capacitor's value is constant. So C into dV by dt. That will be displacement current ID. And the capacitance for a parallel plate capacitor is given by capacitance for a parallel plate capacitor is given by epsilon naught A by D. So in this case, your ID, okay, your ID will be equal to, instead of C, you can substitute epsilon naught A by D. So dV by dt. So this is the another equation. Okay. Right. So this is the expression for displacement current. Okay. I hope you all can understand the concept up to this point. And now we are going to discuss the next concept, that is magnetic field. Okay. So magnetic field due to a uniform but time varying cylindrical electric field. So now, in order to explain this, I will be drawing a circle here. So the cross section of the cylinder, okay. The cross section of the cylinder actually looks like this, circular one, okay. So the radius for this circle is nothing but capital R. Because here electric field is confined to a cylindrical region. The radius of the cylindrical region is capital R. And here I have shown you the cross-sectional view of the cylindrical region. So the radius of that cylindrical region is capital R. Okay. So within the cylindrical region, your electric field is, and the electric field is actually changing with respect to time. Okay, it is changing with respect to time, and I am actually imagining, or I am actually considering a point at a distance smaller from the center of this circle. Okay, I am actually considering a point at a distance smaller from the center. Okay, so from the center, the distance is actually smaller. So at this point P, I have to calculate the magnetic field. For this point P, which is at a distance smaller from the center, I am going to calculate the magnetic field. So here I am having many scenarios. Okay, like the first scenario is the small r greater than capital R. Here, what is the value of magnetic field? B is equal to mu naught epsilon naught R whole divided by 2 into dE by dt. Okay. Why it is dE by dt? Because time varying electrical field. Okay, time varying electrical field is actually confined in this region. So dE by dt. So for R greater than capital R, you will be getting, sorry, R, this is actually R less than capital. So when you are R is less than capital R, your magnetic field is given by this equation. Okay. So here the magnetic field is directly proportional to small r. So along the axis, what happens? Okay, along the axis of this cylinder, your small r will be 0. So in that case, your B will be 0. Okay. So this is the expression actually. B equal to mu naught epsilon naught R by 2 into d by dt. The magnetic field expression along the axis, since your R is 0, your magnetic field is also 0. Okay. So this is one equation. And the second scenario which we are going to consider now is your R is equal to capital R. So in that case, your magnetic field will be maximum. So this magnetic field is represented as B max. So that will be equal to mu naught epsilon naught. Instead of small r, you will need to put capital R. So mu naught epsilon naught capital R by 2 into dE by dt. This is the maximum value of magnetic field. Okay. And now finally, at R greater than capital R. Okay, the third scenario is your R greater than capital R. In that case, what will happen? So in that case, what will happen to the magnetic field value? So that is B is equal to mu naught epsilon naught by 2 capital R squared by small r into dE by dt. Okay, this shows that your B is inversely proportional to small r. Okay, but in these cases, so here your B is actually directly proportional to small r. In this case, your B is actually directly proportional to capital R. But when your R is greater than capital R, then magnetic field is inversely proportional to small r. Okay. So when you plot the magnetic field along y-axis and small r along x-axis, how will you show the variation? So it is actually similar to the variation of electric field with respect to distance. Okay, and we have discussed that also. So here you are having small r along x-axis and magnetic field along y-axis. So how does your graph looks like? And it is like this. So after this point, the variation is like this. I think I can use some other color. Okay. So here, this point, where it reaches the peak, that small r equal to capital R. So in this region, B is directly proportional to small r, and in this region, B is inversely proportional to R. Okay. So in this region, B is directly proportional to R, and in this region, B is inversely proportional to R. So here, R lesser than R, and here R is greater than R. Okay. Do you all understand these cases, students? Do you all understand this? Any doubts you have up to this point?
No, sir.
Anyone having any doubt, students?
No, sir. No doubts.
Okay. If you don't have any doubt, then we shall move on to the next concept. Okay. So displacement current through a capacitor, they have added a few more equations here. So displacement current through a capacitor. So this is the heading for this concept, and we know very well the equation. Displacement current is given by epsilon naught A dE by dt. So when the displacement current is maximum, okay, when the displacement current is maximum, and before that, now we are considering a capacitor having circular plate. Okay, consider a capacitor having circular plate with area of cross section capital A. This is equal to pi r square. Okay, because the radius of these plates is capital R. Because the radius of the plate is capital R. So here, the maximum value of the displacement current is given by epsilon naught pi r square dE by dt. Okay, and at a distance small r from the center, in general, what is the value of the displacement current? That is epsilon naught into pi r square dE by dt. This is the general equation. At a distance r from the center, your displacement current is given by this equation. So when you divide this I of r by I max, what you will get, that is I of r divided by I max. So that will be small r squared by capital R. Okay. When you divide this equation by this equation, you will be getting. Okay. Right. So now we will be moving on to the discussion of Maxwell equation. So there are 4 equations given by Maxwell, and you may be getting numerical problems based on these equations. So the first equation is integral E dot ds, that is equal to Q by epsilon naught. Obviously, this is Gauss law in electrostatics. And number 2, this is Gauss law in magnetism. So integral B dot ds is equal to 0. Okay. So this is the Gauss law in electrostatics, and this is the Gauss law in magnetism. Okay. So this is Gauss law in electrostatics, and this is Gauss law in magnetism. And the next equation is Faraday's law of electromagnetic induction. So that is integral E dot dl is equal to minus d phi d divided by dt. That is the induced EMF. Okay, that is given by E dot dl. So this is actually Faraday's law of electromagnetic induction. And finally, the fourth equation is integral d dot dl. That is the Ampere's circuital law. Just now we have discussed. So mu naught into IC plus epsilon naught into d phi e by dt. Okay, this is modified Ampere's circuital law. This is modified Ampere's circuital law. So these are the 4 equations given by Maxwell, and when you know all these equations, you will be able to solve numerical problems. Okay, right. Now we shall move on to the next concept. Okay, that is so far we have discussed the properties of displacement current and Maxwell's equation. All these things we have discussed, and now we will be discussing the electromagnetic waves actually. So electromagnetic waves. So we have various properties of electromagnetic waves. So I am going to give you some important properties. That is, electromagnetic waves are produced when you have uniformly moving charges. So uniformly moving charges, or I can call it the other way. So if you have a charge, okay, 1 second student, I will be back. Yes, students, we shall continue now. So we are going to talk about oscillating charges. Oscillating charges means a charge is oscillating with some frequency. Okay. So due to the oscillation of the charges, you will be getting oscillating electric field. And the oscillating electric field generates oscillating magnetic field. Okay. Oscillating electric field produces oscillating magnetic field. Okay. So the oscillating electric and the magnetic field actually generate electromagnetic waves or EM waves. So due to the oscillation of charges, you are getting electromagnetic waves, and frequency of these EM waves. Okay, frequency of these EM waves. EM waves means electromagnetic waves. So frequency of these EM waves depend on the frequency of oscillating charge, or it actually equals. Okay, frequency of this EM wave actually equals the frequency of oscillation of the charge. So now I am giving you the formula for the velocity of electromagnetic wave. How can you calculate the velocity of electromagnetic wave or EM wave? So that velocity is given by T equal to 1 by square root of mu naught into epsilon naught. So this is the velocity of electromagnetic wave in free space. Okay, in free space. So using this formula, if you calculate the velocity of light, you will be getting 3 into 10 power 8 meter per second. Okay. So the electromagnetic waves are actually transverse in nature. So this is another important property. Electromagnetic waves are transverse in nature. Okay. EM waves are transverse in nature. Okay. Now I will be giving you some equations regarding the electromagnetic waves. So you carefully observe all these equations, which will be helpful for you. So the average energy density. Okay. Now I will be giving some equations. Energy associated with electric field in EM wave. So in an EM wave, you have the following equation. Energy associated with electric field. So that is given by UE equal to half epsilon naught E square. Okay. And energy, it is actually energy density. Okay. It's not just energy, it is energy density. So energy density associated with electric field is given by UE equal to half epsilon naught E square. Then energy density associated with magnetic field it is given by UB equal to V square. Okay. So UB equal to V squared by 2 into mu naught. This is another equation. And now the total instantaneous energy density. Okay, the total instantaneous energy density in EM wave. Of EM wave it is given by U equal to UE plus UB. So that will be half epsilon naught E square plus V square by 2 mu naught. Okay. So the average value you can find out from this equation. For over a long period of time, if you want to find out the average value. Okay. So average value of energy density over a long period of time. total energy density over long period of time. It can be represented by U average. Okay, U average is equal to 1 by 4 epsilon naught E square. I am not deriving it, I am actually giving you the final expression. Okay, so 1 by 4 mu naught B square. This is the average value of energy density. Okay, so this is another equation, and we have few more equations. The intensity of EM wave. Now I will be giving you the equation for intensity of EM wave. Its intensity is nothing but energy crossing per unit area. Energy crossing per unit area per unit time. Perpendicular to the direction of propagation. Perpendicular to the direction of propagation. This is called intensity. And what is the expression for intensity? So I is equal to half epsilon naught E square T. T is the velocity of EM wave. Okay, small letter c. And this is also equal to, okay, and this is also equal to half T squared by mu naught into T. Okay, this is the expression for intensity of EM wave. And then the next concept or next equation which we are going to discuss now is momentum of EM wave. Momentum of EM wave okay, momentum of EM wave. So here we have two scenarios. The first scenario is if wave is incident on completely absorbing surface. Completely absorbing surface. Then your momentum is given by P equal to U by C, where U is the energy divided by C is the velocity of EM wave. Okay, this is the expression, and P equal to U by C, where U is energy. And the next case is wave incident on totally reflecting surface. Totally reflecting surface. So in that case, your momentum is given by 2U by C. This is quite obvious because whatever energy is falling on that surface, it is reflected back. So it is twice the energy. So P equal to 2U by C. Okay. And the next important definition is pointing vector. Next important definition is pointing vector. What is the meaning of this pointing vector? So it is the rate of flow of energy. Rate of flow of energy crossing unit area per unit time. Crossing unit area per unit time. It is called pointing vector at a point. Unit area per unit time at a point. It's called pointing vector. So that is represented by vector. So vector here is equal to 1 by mu naught. So within the bracket, vector E cross vector B. So that will be vector E cross vector H. So that will be equal to c square, where c is the velocity of light, c square epsilon naught into vector E cross vector C. Okay. This is the expression for pointing vector. The SI unit for pointing vector. Okay, SI unit for pointing vector is watt per meter square. So now the average value of pointing vector we are going to discuss. The average value of pointing vector. That is given by, okay, so this symbol represents the average value, that is represented by C B naught square divided by 2 mu naught. This is one equation. And another equation is half epsilon naught E naught squared into C. Okay, all these formula are applicable for average value of pointing vector. Okay. Now I will give you some formula related to radiation pressure. So radiation pressure means radiation falling on the surface actually imparts momentum to it. Okay, and due to the momentum you are getting some pressure on the surface. That is called radiation pressure. So for a perfectly reflecting surface, your radiation pressure is given by 2I by C. That will be equal to 2S by C. Where S is the pointing vector and C is the speed of light, I is the intensity. Okay. And for a perfectly absorbing surface, we have P suffix A is equal to I by C. That will be equal to S by C. These are the equations for radiation pressure. Okay. And you all know very well about the different types of electromagnetic waves. Okay. So what are the different types of electromagnetic waves? And different types means we have radio wave, microwave, radio wave, microwave, and infrared wave, IR, and visible rays. Okay, visible light or visible. Okay, and UV rays, ultraviolet, then X-ray. Okay, X-ray and gamma rays. These are the different types of EM waves. Okay, so all these waves have their own wavelength range and their own frequency range. Okay, so based on the frequency range, you can identify, or based on the wavelength range, you can identify the type of radiation. Okay, and all these things are important. So these are the important concepts in electromagnetic wave, and all these formula, if you can keep in mind, you can easily solve the numerical problem. Okay, so now we have come to an end to this lesson of AC circuits and electromagnetic waves. Next class, before next class, I will be giving you a test containing multiple choice questions. Okay, everyone should attend the test and be prepared for the test. And you will be getting the question paper most probably on Saturday. Okay, on Saturday you will be getting the question paper. So please, everyone attend the test sincerely. And that's all for this session. Thanks for joining this session, and we shall keep it this much. We shall meet again in our next class. Thank you so much.
Thank you, sir.
Thank you, students.